Friends, welcome to my channel once again. Today we are going to discuss a topic called intakes. Geometrical details of intake. Depending on the entrances, we have divided it into two categories: single entrance and double entrance. Depending on the speed, we have divided it into two categories again: subsonic inlet and supersonic inlet ducts. Intakes. A well-designed intake is essential to allow the aircraft to maneuver to high angle of attack and side slip without disrupting flow to compressor during cruise. The inlet is so important to overall aircraft operation. It is usually designed and tested by the airframe company, not the engine manufacturer. As inlet operation is so important to engine performance, all engine manufacturers also employ inlet aerodynamists. Complex designs of intakes. Here we will be having curved intake. In order to decelerate the air, we will be choosing a long path or we will be choosing a curved shapes so that air will get decelerated fastly. Then we will be having twin intake where we will be having two entrances, air inlets, and these two air inlets will be guided into the single or merged into a single intake, so that we'll be having higher amount of mass flow rate. Then we'll be having submerged intakes where these intakes will be submerged into the aircraft itself. Then we'll be having supersonic intakes, that is ramjet or scramjet, where we'll be using sharp edges in order to form shock waves. Design steps for intakes. Only supersonic flights decide and optimize number of oblique shock and final downstream conditions of normal shock. For both subsonic and supersonic flights, we need to compute all properties at the just upstream of inlet. Then for subsonic flights, outer cone affected ambient air properties and flight Mach number are upstream conditions for inlet. Define upstream inlet conditions as a function of pressure, temperature, and velocity. Then we'll be having cycle calculations demands a mass flow rate. So mass flow rate can be given as rho AV as a function of x, that is distance. Area of x can be given as m dot by rho v, that is equal to m dot rt of x divided by pv of x. Exit conditions for inlet. Achieving the required exit Mach number. Constraints are limiting the exit dimensions, limiting the length of the inlet, limit on the pressure recovery factor. Exit conditions for nozzle can be given as ambient pressure or back pressure. The constraints are limit of pressure recovery factor. Step-by-step design of intake or nozzles. Select appropriate value of dx. Assume that all properties remain unchanged over the length dx and same as inlet condition. Therefore, we'll be having a formula called this one. Then, of design aerodynamic of inlets. At ground conditions, we'll be having this type of flow, and as we move at climbing speeds, there will be a change in pattern of the flow, and then at high speeds in cruise condition we'll be having a jet formation of jet, and then in top speeds a complete jet will be formed where there will be circulations formed at the inlet jet. Aerodynamic performances of subsonic intakes. Subsonic intakes exhibit four different flow regimes or stall characteristics as we have seen in above four diagrams. Non-dimensional axial length or length, inlet area, and the total divergence angle of the diffuser are chosen as the primary variables to identify the flow regimes. Fully attached exit flow with steady internal flow, fully attached exit flow with internal unsteady flow, fully developed stall flow, and then jet flow. In first diagram, we have seen fully attached exit flow with steady internal flow and fully attached exit flow with internal unsteady flow. So here we can see this one at ground conditions and climb conditions. Then at cruise speed conditions, fully developed stall flow can be seen, and at a maximum speeds we will be finding jet flow. Flow regimes in subsonic intakes. A fully attached exit flow with steady internal flow. Fully attached exit flow with internal unsteadiness, that is the transitory stall regime. Stall patch and stall patch appears. Fully developed stall flow where we'll be having dividing streamline, and in jet flow we'll be having large stable vertexes where dividing the streamlines. Quantification of irreversibilities in intakes. The amount of disruption of a flow is characterized by numerical inlet distortion index. Different airframe use different indices: diffuser efficiency, ram efficiency, pressure recovery factor. The performance of intake depends on various geometrical and dynamical parameters, namely exit to inlet ratio, shape of the inlet, angle of turn of the limbs, length of the duct, inlet Reynolds number, Mach number. Spillage drag. There is an additional propulsion performance penalty charge against the inlet called spillage drag. Spillage drag, as name implies, occurs when an inlet spills air around the outside instead of conducting the air to the compressor phase. The amount of air that goes through the inlet is set by the engine and changes the altitude and throttle setting. The inlet is usually sized to pass the maximum airflow that the engine can ever demand. For all other conditions, the inlet spills the difference between the actual engine airflow and the maximum air demanded. As the air spills over the external cowl lip, the air accelerates and the pressure decreases. Spillage drag model can be seen over here. At station number 1, free stream can be observed, and from station 1 we will be having inlet lip, from station 2 we will be having compressor entrance. Spill drag model is similar to thrust equation, so here we will be having d spill as k of m dot air v1 minus v0 plus a of p1 minus p0, k where k is lip suction factor. With this we'll be winding up the video. If you like the video, please do like, share and subscribe.